Wait, ask me this kind of question. I don't know. Is it air?
No, it's not.
Then you cannot. That's why you cannot. I went through all these things before, right? Yeah. What the hell, man? Ah. Huh?
Yeah, it's always smaller. Always yes.
Yeah, yeah, okay. Oh, okay. I never thought you all that like in that way. So I don't know. Right? It's like n1 sine 90 equals to n2 sine c. Right? That's what I remember myself. Yeah. But like once you rearrange it, maybe it's smaller or bigger. I don't know. But I never say that like that. When I say the sine I over sine r is always sine bigger over sine smaller. You get what I'm saying? Right? That's why when you say smaller over bigger, I was like, I don't remember that. I don't remember saying that. Yeah. Yeah, yeah, sure. Who? Who's coming? Who's not coming? Yeah, that's fine. Let's just go. The rest of them are online. They've been all like uh no, I wanted to inform you all that next week there's no official lessons. But the week after there is. Right? So what happens is this. I'm gonna just throw out a head count after tomorrow's paper that eh? Why is it not? What? Yeah, no papers next week. Yeah, wait, hang on. So yeah, I am. He went home. So how do you tell the time? He didn't tell the time. You go by feel.
No, the exam said 30 minutes.
Oh shit! Oh shit! Half an hour left and you're on the first paragraph. What the freak, dude? Hey, listen. So I wanted to inform you all that this coming weekend, right? This coming weekend, there's no official lesson. All right. I'm still gonna hold a Sunday and Tuesday one, right? It's more or less like catered for the SGI side of things, right? I mean, there's this not actually not really SGI. It's catered for those who join late, like those who like join like I don't know earlier this year, like not last year, right? No, so during this time, right, I will go through things like circular motion. Huh? No, yeah, I know. So circular motion, or maybe even topic three, or stuff like that, right? Topic three being the ideal guess and all that. But I'll do a head count first. If the number of people who want to get those lessons, right? It's more than the Sunday or and Tuesday's class, right? Then I'll open up, let's say maybe the Saturday, or open up the Monday's class, right? It's just that this coming weekend, this coming weekend, this one here, sorry, the 24th to 28th, there's supposedly only 2 days of lessons, which is the Sunday and the Tuesday, the 25th and the 27th, right? That means for the ACSi guys, I'm saying don't come. But because the SGI side of things, right, there's a few of them who joined very late. They joined like in July only, and they kind of like they need a little bit more help. So I'm holding the lessons then, right? We still have a lesson on the first weekend of the SEP halls, right? There will be a proper lesson, right, on the first weekend of SEP halls. There will not be a lesson on the second weekend of SEP halls for the ACSi guys, right? The second weekend is like no untouchable for you guys. You understand why, right? Because that's just like before your other papers. So for us, for you guys, I will be holding the official lesson here, right? But there will be one lesson this coming weekend. It's just that I'll ask an open question and see who wants to join into those classes. If the numbers spill over, that means more than the Sunday and Tuesday's class, then I'll just open up another day, right? Otherwise, I already made plans to I already like have taken out of it from my calendar not to do the Saturday, Monday, and Wednesday's class. Okay, then but really depends on who wants what. Okay, yeah, and but I'll tell you what I'm gonna go through. Okay, I'm gonna go through this one here on this timing here, right? Maybe one of the things I have not gone through before, like for example, thermal, ideal gas, right? Yeah, ideal gas stuff, or maybe the topic 8, the nuclear reactor stuff, right? Because I was waiting for the SGI side of things to finish their syllabus. Then I can start teaching it, you see. And they have finally finished it. So yeah. All right. And don't forget, we still have to revise for 7 and 12. Right? 7 and 12, the Feynman diagrams and all that. I mean, we did it in May, in the whole stretch of April to May, right? But we didn't really have time to go and revise, right? Those topics, right? So the ones that are still left, right, will be the 3, 8, 7, and 12, right? 3, 8, 7, and 12. Now, if we have enough time and if I sense there are still like problems going on, then it's either 10 or 11. 10 or 11. Option imaging no, so imaging will be additional, like not additional. I will just hold it as a separate session for your, right? Especially when your school break starts, when your study break starts, right? Once your study break starts, I can use whatever time you have, right? I can abuse your time, right? So for those kind of like extra stuff, right? Let me deal with it, like once your study break starts, all right? Which is when again? ACSi, when does your study break start? What's that? 5th of October. Like 5th of October, is it? When does the actual paper start? Yeah, right. See, right? If you tell me it's 24th, right? That means I got these 2 solid weeks here to give you any extra things that I need to give you. You know what I mean? That means you go for your regular lesson. Then if let's say no, maybe I just hold one day for like an extra, right, for to help you with the topics, and that's like up to you whether if you feel that you're strong for the topic, then don't attend, right? It's not counted as a lesson. It's just extra stuff. Yeah, it's not counted as a lesson. Actually, I'm stupid lah, right, in that sense, right? So I hold extra stuff, but I don't count it as a lesson, right? So it really depends, right? During these 2 weeks, your study break. I'm a what? I really have no idea. I'm a bit shocked myself. I didn't know he was closing. Like I just met him like earlier this year, and I just thought like, oh, like why don't I do something for my students and all that. But I had no idea that he was having plans to close a retail shop. He's still doing online sales and he's still doing delivery to like his customer, like some hotels buys his ice cream. So he's still doing those. But the retail side of things, the Holland Village outlet is, I think it's just the rental is just bleeding money lah. So yeah. Case in point, I cannot rent that place. Huh? It is, right. Yeah. And the worst thing is that right beside he's right in the middle of the other two, right? Birds of Paradise is one side, Daily Scoops is on the other side, and they are so much more accessible than his, right? And from the outside, you can't even tell that Island Creamy is upstairs, right? I wanted to tell him to get a neon sign, right? I wanted to tell him that like maybe 2 or 3 weeks ago. Then now I realized, oh shit, okay lah, no need already. He already has decided already, so it's like, oh no, yeah, I feel so bad though, yeah. Right. So go ahead and just please, right? And my expense, yes, please go and use the vouchers, right? By this Friday, Saturday, right? I'm quite sure it's gonna be very crowded actually. Cause like if all those regulars know that he's closing down for real, then I think all the old timers will still go lah, right? Old timers, okay, old timers. Okay. Yeah, old timers. Okay, hey, let's put some order to it, right? Let's not waste everyone's time. Okay, it's gonna be a bit messy, right? Because I myself never put an order to it. So we're gonna start with the ACS prelims first. Okay, yeah, don't worry. So we just do whatever, who needs what. I will make sure there's enough time for the other things. Okay, all right. Otherwise, you all go home first, and then the next session is 5:30. Then I'll tell them I'll do the other thing first. Then you all can log in. Right, that sort of thing. Anybody has econs tomorrow? Shit lah, why all the econs people here? Tomorrow, there's no BM, right? There's BM also? Oh shit, so it's just both BM and econs, is it? Okay, alright, everyone's just cooked, huh? Damn. Okay. I thought it was just econs only. Oh, I didn't know about BM. Okay, let's just make the most out of it. Come. ACS past year papers, year 6 prelims. Which year is that? 23. Do I have the 23 paper? Yes, I do. Paper what? 2 lah. Right? Not like you're gonna do 1 and 3 now, right? Hey, open up there. Okay. No, then the next thing is this, right? Paper 1 and 3, okay? No, okay? 3 is like that. 3 is okay. 1 is tough, is it? Is the first 20 question as hard as they say it was? Really?
He said he screwed up. He said he missed 4 questions, then he screwed up.
So he's going to take 36 lah.
Yeah. To me, the last 20
Right, it's usually those who say that those are the questions easy one will get it wrong. Really? Okay. Then what have I been doing for you then? What? I went through before. Oh, a lot of them are repeated questions from the ones that we did before. Then why? Why are you all messing up? No! No! No, guys, no, which is why I never make you all do any prelim papers. Which is why I never make you all do any of the prelim papers, because I wanted you all to do the IB papers way earlier so that you don't get overwhelmed in the next 1 month. You must understand, in the next 1 to 2 months, you guys might be like, oh shit, I got so many papers to do, right? That's why I wanted you to start early. Okay, never mind. Let's start. Okay, all right. From the prelim 23, anyone online even, okay? Don't try to DM me. Just chat it in the group chat because everyone will be able to see it. All right, just let me know what you need from the November 23 if you did it. Question 5C and D. Do you have the, oh, you have the paper with you. Okay, you got a soft copy. Everyone has at least a copy of it, right? Question 4. Online. Come on. Right? It's a buffet. Come. It's Buffett. Then it's Warren Buffet. Alright. Okay, you guys take your time, alright? I'm gonna do this, okay? Alright, let's go. Do y'all see that other question I posted? That momentum question I sent you all? That was wild, man. That one. Where was that?
So you send an aeroplane one.
You saw me send aeroplane one.
You send it as an aeroplane.
There was this like really interesting question. This one. This is damn funny, This one here, right? It stumped me for a few weeks. It was like no. I know it's MCQ, no. But I mean in the spirit of topic 2, okay? So it stumped me for a few weeks because like when I was trying to do this, right, I was like trying to calculate the how many times the thing bounced back and forth. I was trying to calculate the distance, calculate this and that. Wow, in the end, right, it's just a stupid question. If you give this block initial velocity with this mass m, right, and it collides with this outer block, and the outer block moves back and forth, whatever it is, right? So it collides and then it starts bouncing back and forth, that kind of thing, right? The idea here is at the end of the day, right? At the end of the day, once this block has transferred all its momentum to the big box, okay? The final momentum, if you assume all elastic collisions, right, it's just the same momentum as before, which is just m times v naught, right? Which is damn dumb, huh? Like it's just m times v naught. No, but then the final speed of the block and the box, right, will be you have to find the momentum divided by the combined mass. Yeah, and that was it. That was it. Like there was no like complicated calculations of like back and forth. Just to remind you that initial momentum of the system must be conserved, right? Again, I think that was the one thing that I did, in the topic 2 revision. What other thing that I said recently that I kind of like forgot that I wanted to do? Damn it. Okay, all right. No, please, that shouldn't be an option at all. Okay, question 4. We got a request for question 4. Question 4, right? If you have never done this paper before, right? But just remind you, this is prelim 23. It is very unlikely it's gonna come out again, right? Maybe not even a version of this. No, but seriously, I've seen all the prelim papers. I keep looking at all the prelim papers back and forth, and I realize that they don't really repeat the questions, right? Which is quite, I guess, professional of them, right? Which is rare, right? Which is rare. But yeah, there we go. All right. Okay, what's your question here? Sorry. Part B, is it? Huh? Okay, so you got a battery with internal resistance, you got a switch, you got external resistor, you got a voltmeter across here like this. I did topic 5, right? Recently? Yeah, I did topic 5. Okay. Then they ask you, deduce the internal resistance of the cell, right? Okay, that one we find. Then in another circuit containing two secondary cells, an ideal voltmeter shown below. Oh shit. Okay, what? Okay. Yeah. All right. So this is like, whoa, what's happening here? You have a cell here, and then you have another cell there. There's no other resistor, right? There's a voltmeter in between. So what's going on here, guys? Can anyone describe a real life situation for this? Real life situation for this? Yeah, your power bank and your phone, right? Your power bank and your phone, right? It's basically what's happening here. Your power bank has 12 volts, your phone has 6 volts, right? You're trying to charge your phone, okay? Right? The power bank has its own internal resistance, the phone has its own internal resistance. So what happens here is that there will be a current flowing, right? And the current is flowing this way, this way, this way. And what happens is that this 6-volt battery, right, being charged will eat up 6 volts. So it'll be like, as you go here, it will be -6, right? Then whatever current that passes through, whatever current here you have, then this is like 2i, right? The voltage eaten up here will be 2i as well. Okay, then the current goes back to the other battery here, and then this one here will be like 1i, right? 1 times I, that will be the voltage that this guy, then you plus 12 again. So it's like one of those games whereby every time you cross here, right, you plus 12, then you travel, then you -6, then you -2i, travel here, then -1i, right? That sort of thing. Okay, right? Then you end up like being 0 again. Okay, and your job is to determine I. What? Well, you can do Kirchhoff. I guess you can do Kirchhoff. Yeah, but there's only one loop. Yeah, there's only one loop, and there's only one current, right? So I mean that was it. Like the supply is 12, so you would write down 12 equals to, right? Then you can put a -6 also because it goes against the battery, right? So you can put a -6 here, right? So you can put a 12 plus -6, 12 minus 6 equals to, right? This guy will take up 2i, right? And then this guy will take up 1i, like that, right? And that's it. That's your answer, right? So nothing too complex, but you can find I. Okay, can? Right. So yeah, in case you were wondering, right? So when you charge a battery and the EMF is 6 volts, it's gonna eat up 6 volts. So you put a 12, then you plus a -6 because you're going against the battery's direction. Okay? Yeah, yeah. That's the thing. Okay? Is that the question? No, that's not the question. Shit. Okay. Oh no, sorry. Ha ha. Okay. Reading of the voltmeter. Nobody wants to ask this. Anybody? You want to ask it? Okay. So what's the reading of the voltmeter then? Ooh. So think of the lesson I gave the last time round. Like how do you find the reading on on the voltmeter? How, like, what does the voltmeter do? Potential difference between where and where? Between this point here and this point here, right? So the question is, what's the voltage here? What's the voltage here? Here is 12, right? So down here, this, no, wait, this 12, right? This 12, then this one here eat up 6, but then this internal resistance eats up some. What's the current, by the way? But the current is 2 amperes, is it? So the current is 2 amperes, right? So how many volts does this guy take up? Yeah, 4 volts, right? So you -6 minus 4, and then you're left with 2 volts here, right? Then the voltmeter reading would read 10 volts, right? Right? Then the voltmeter read 10 volts. That's the answer, lah. Right? Yeah, yeah. You should use that method I told you. Okay, right? The potential, the point method. This one. You're asking about this? Okay, 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 okay. I'm a bit concerned about this statement though. Right? It's constant. the current in coil P is constant. So if the current in coil P is constant, right, would coil Q, based on this, experience anything? No, wait, hey, shit. I'm talking about when the current in P is constant, right? Is there anything happening to coil Q? Nothing, no thing, right? Yeah, no thing. Okay. Because there's no change, right? Then you go and insert an iron rod into coil P, right? So you go and insert an iron rod in coil P, right? That sounds wrong, right? Okay, insert an iron rod into coil P. What does that do? What does inserting a rod into coil P do to, coil P? No. What does it do to coil P? Yeah. I mean, I know the question is asking for coil Q, but I'm asking what happens to coil P. Yeah, the field lines are concentrated, right? So I need to show you before it got inserted in, right? The field lines will look like this, right? The field lines will look like this, right? Like that, right? Okay. Now, which direction is this? I don't exactly know because they didn't tell me the direction of the current. Can right? So okay. Let's just put it there with no direction first, all right? And then what happens is that once you insert the rod, the field becomes stronger, right? The field becomes stronger. So once you put this iron rod in the middle like this, okay, then the field becomes stronger because stronger together, right? Yeah, yeah. Malaysia boleh, right? So now the field lines are now closer to like is one. So the question is, what does this guy experience then? Does he experience a change in flux? He does, but it's still the same three lines. But it's still the same direction too. So, but he experiences a change, right? So what happens is that for coil Q thinks that the field has become stronger. I mean, not that he thinks, he experiences a stronger field, right? So there's that change for coil Q, right? So if let's say, for example, the field lines are pointing right to the right from coil P, for example, right? As an example, huh? Okay. What will coil Q do now? Yeah, it will try to, right? It will try to create field lines at points where? Right? Yeah, you'll try to create field lines that point this way, right? Because it's trying to oppose the change, right? That's the change, right? You insert the iron rod, the field becomes stronger. Coil Q will try to oppose the change. Okay. However, they didn't really need you to talk about the direction, right? They just kind of like saying that during the time that the rod is moving, there is a reading on the voltmeter connected to coil Q. So your answer will be a bit more generic for 2 marks, right? It will be something like this. When you insert the iron rod, right, the field lines are concentrated in the iron rod on coil P, right, making the magnetic field of coil P stronger, right? Therefore, coil Q experiences a change in the flux, experiences induced EMF by Faraday's law. Please don't talk about induced current. Okay? There isn't any induced current. Okay? So I mean, because the voltmeter is there. So what happens here is that the induced EMF in coil Q will be in a direction that opposes that change, and then you just leave it as the answer, can already. Right? That will be good, right? So there's no need to that I don't know whether you'll be marked down if you write current. Because there's actually no current when there's a voltmeter here like this, because the voltmeter blocks the current, right? So you can talk about the induced EMF and how the induced EMF direction opposes the change that it experiences. Right, so coil Q experience, okay, so what happens to coil P? Stronger magnetic field, then Q experiences change in magnetic flux, right? Then what happens to, there will be, based on Faraday's law, right? Quote Faraday's law, please, right? There will be an induced. Yeah. I mean, yeah, is in like quote the word Faraday's law by Faraday's law, right? Coil Q will experience a induced EMF, and the direction of the induced EMF is such that it opposes the change, and therefore there will be a reading on the voltmeter. Like, get to this point, get to this point. There's no need to go and talk about, oh, it'll be in the opposite direction, it will be like, facing the other side, it will be like, if let's say this one is facing the left, then this one also be facing left. Don't need all of that, right? We don't need all of that. We just need you to come to the point whereby there's a reading on the voltmeter. That's it. Okay? All right. Okay, so that's for 4B. Part 2. You're asking about the part 2, is it? Wait. Are you done with this? This one done already, yeah? Okay, so then there's a part 2, right? So now they tell you that the coil P is now varied, right? The current in coil P is now varied, as shown, right? So how is it changing? Can you kind of like tell me how is it changing? Like, describe how is it changing for coil P? Yeah, the current, yeah. The first part. Talk about the first part first. There's an increasing current, right? Okay. So what's happening to the flux of P? It's an increasing flux, right? So what happens to what Q experiences? So Q, where's my pen? Don't I have a pen somewhere? Oh yeah, okay, sorry. Yeah, so let's reset this thing here. Right. The current of this guy, right? The current of this guy is increasing, right? The current is increasing. So what happens to the flux density of this guy? Flux density is increasing, right? Right, it's increasing at a constant rate, right? So what happens to the coil Q, like, change in flux? Right, so I mean, it's changing, right? So it's changing by constant rate. Is it constant? How do you know it's constant? Yeah, because the change is constant, right? The flux and the current is increasing, right? So the flux linkage here, right, for coil Q is increasing, right? Okay, and we know that the induced EMF in this coil is negative d phi dt, right? d phi dt, negative d phi dt, right? Okay, all right. So then if that's the case, right, that's the case, then what we do is they want us to draw the voltmeter reading, right? Okay, so since it's a constant rate, then the induced EMF here is constant, and I'll put a negative to it. Right, I'll put a negative here. I'll put it as a negative constant voltage first, like that. Right, so I'll put a negative constant voltage here. You okay with this? Yeah, so it doesn't look like straight line. Sorry, my side here parallax error very bad. Okay, like that. Okay. Okay. What? Why? 4 marks? The hell? Oh, why? Why is this worth 4 marks? They're so lazy. Because if it's not these 4 marks, then you have to come up with more questions to fill up the marks, right? Okay. I think, but the scary part though, the scary part is this part here, right? This part here. So there's a very steep change. There's a very sudden change in the current in P. That means it went from a positive current, right? It changed drastically to a negative current, right? So there's a negative gradient here. So I would expect the voltmeter reading here to be a positive value, right? But it's so steep, and it only lasts for a very short amount of time. Like for example, like if you look at it, it kind of like happens from here to here only, like that. Okay, so I would imagine that the EMF will suddenly shoot up to a very positive value, higher than normal. Okay, then immediately after it shoots up, after this gradient is a very steep negative gradient, therefore you get a very positive value for voltmeter. I would imagine that the last part here is actually 0, right? So it'll go back down to 0 volts, like that. Right? Is that the answer key? Yeah, it is. Yeah, I would imagine that would be the case. So you kind of like have to spot how tight this time is, right? And then you just replicate that time here. Like that. Let the voltage spike up like this and then drop down.
It's not a straight line.
No, yeah. Slanted, a bit slanted, yeah, it's fine. Yeah, because the last part here, there's current, but it not changing.
Yeah, no, like
Then I'm trying to explain. So this last part here, the coil, right, is there's no the current is steady, the magnetic field of P is steady, so Q experiences no change. No change means no EMF, so therefore it drops down to 0. Okay, yeah. Okay, I mean, give credit where it's due. This is a good question lah, but it's not worth 4 marks. It's worth 3 marks. Yes, Emily. Yep. Huh? A really skinny triangle. Yeah, yeah, yeah. I think they wouldn't fault you for that. So the question online is this, guys, right? So it's like, why, like, what happens if I were to draw something like this, like, it's a very, very skinny rectangle like that instead, right? Totally fine. Nobody's gonna fault you for that. It will be the same. Same thing, no difference. I don't know. Yeah. I honestly think there's no difference. Like, on the if you zoom out of the graph, it look like triangle. You zoom in, it look like rectangle. Right? But what does the answer key show? It doesn't show anything.
It's just lines of description.
Lines of description. They would rather type it out than to draw it out. What's wrong with them? Okay, fine, right? So anyway, it's like that, like that. Tell them, inform them if they need to draw anything, right? Inform them that Microsoft Edge, right? You can edit PDF, right? Microsoft Edge, okay? Right? You can annotate on the PDF. I'm using Edge. I'm not gonna gatekeep this shit, right? It's right there, right? Look at the icon, right? It's Microsoft Edge, right? One of the best things that have come out from a Microsoft browser since Internet Explorer. Huh? Edge, yeah. Edge is always good. Huh? Okay. All right, next one. What do I need to go through? 5, C and D, is it? 5, huh? Okay. Listen up very closely. I'm gonna think that something is gonna come up from topic 10 in your paper 2. All right. Now this is not me spotting though. Okay, not me spotting, huh? All right. So if they ask you for escape speed of a orbiting satellite, that means it's already orbiting. Okay. If they want you to find the escape speed of this satellite, check the total energy. Right. I think I sent that out in the group chat. Right. I sent that out in the group chat a while back. Right. Check the total energy. Let me just show it to you. Let me just show it to you. Do y'all find it? Can y'all find it? I don't know where is it. Like there's 270 pictures in there. Like, shit, I keep sending you all pictures, but y'all nobody reply. You know how lonely that is, or not? Especially when I send you guys stuff at 2 a.m. right? Then no one replies me. I'm so sad. You send GIF to me. Shoot, I don't know where it is. It's in one of those pictures though. It's in one of those pictures. Okay, alright, I'm so bad at this though. Where? Does anybody know where I'm talking about? I see my own face there. I see the ice cream vouchers. That's way too early, really. They were. What? Oh, yeah.
I asked you a question.
I don't know where I am at. I don't know where I am at. Okay, it's somewhere there. Alright, anyway. Alright, so if it's an orbiting satellite, check its total energy, right? So you know there's an equation for total energy for an orbiting satellite. It's basically negative half GMM over R. Okay, negative half GMM over R. Watch out for the big R and the H, right? Or you take the entire R here from the center of the planet, right? I'm quite sure you all are aware of that already. I've repeated that quite many times already, right? So let's say, for example, you know the total energy of a satellite, right, is what? I'm just gonna write this down. Total energy of a orbiting satellite, right? Total energy, right, of orbit. Okay, of orbit. Now the key phrase is to check whether it's in orbit. Total energy of orbit is what? Is negative half GMM over r, right? Where r is the, like, you know, if let's say this is big R and this is h, right? R plus h, right? So how do you get a satellite to go to infinity? You give it that amount of energy. You make its total energy 0, then it can escape, right? If they convert this to some sort of like electron orbiting around a nucleus kind of question, same thing, right? If it's an electron orbiting around a nucleus, right, which is static electricity, right? Okay, how much energy do you need to give the electron to escape, right? Orbit, right? I know that's ionization energy, guys. I know that, right? But that's, yeah, I know, right? But that's like literally negative half KQQ over R, right? That's like half of the EPE, right? Yeah. Okay, so it's the same concept here, right? You make the total energy 0, it will escape, right? Let's tie this in with topic 7. You know your energy levels for hydrogen? You know your energy levels hydrogen? The what's the n of the ground state? N is equals to what? N equals to 1. N equals to 1. Right? N equals to 1, N equals to 2, N equals to 3, N equals to 4. Right? what's the energy level? What's the energy value of this thing here? You know the number, negative 13.6 eV, right? Okay. For hydrogen only though, this is for hydrogen only, right? For hydrogen only. Do you know that you can actually calculate the energy levels for hydrogen at every level? Which one? Which equation? Where? Bohr's equation. Bohr. All right. Niels Bohr's equation. Topic 12. Right. You can use the energy level and go and calculate every energy level there. Do you understand that? All right. That's only for hydrogen. That's only for hydrogen. All right. That's only for hydrogen. Yeah. It's somewhere. And I have it here. Don't worry. Just have it. I have it here. I have it here. There. There. Yeah. Oh, what's up? Yeah, yes. Like you need to increase this V until that escape speed, then it can escape. You get what I'm saying? You don't add the V escape, you give it that V escape. Right? That means the speed must be that escape speed that you calculate from giving the total energy there, like that. Okay? Alright. Then one more thing regarding G fields and E fields. This is from topic 10, right? This surface, I think yesterday, I think one of the MCQs I was doing, right? Potential gradient gives you what? Potential gradient gives you negative of field strength, right? It's by definition, right? It's by definition. It's just that we usually for calculation we don't give a shit about the negative sign, but it's there, right? So potential gradient is negative of field strength. It was an MCQ question. It was an MCQ question. Option C and D, right? Option C is the potential gradient gives you the field strength. Option D is potential gradient gives you the negative of the field strength. Right? D is answer because there's a negative of the field strength. Yeah, it's by definition, right? It's there. All right, so super annoying. It didn't come out right. Okay. All right. So that's for this little part here like this, right? So yeah, just remember that if you want it to go away to infinity, you make the total energy 0. Okay? Okay? Okay. No. What's your actual question? Sorry. Option 5C, is it? 5C. Okay. All right. No, this is the picture that I sent. I don't know whether I don't know. Yeah, I don't know. Okay, never mind. Since all of y'all here, right? I'll go through this now. Okay. No, it's okay. Question: is this object gonna be able to escape? No, it will go to a certain height, right? But what will happen next then? If you don't do anything else to it, yeah, it will just come back straight down, right? So you don't give it, right? So for satellites, right? You know those satellites that orbit around Earth, right? Do you give them V escape? No. Why not? Yeah, we don't need them to. No. As in V orbit is when it's orbiting, right? But the launch speed is a fraction of the escape speed because you don't need it to escape. I want it around Earth, right? So I don't need to give it like escape speed. I just give it like a fraction of escape speed. This one here is this probe, right? Is launched with half the escape speed. Okay, and therefore, what is the launch KE then? Like let's say we draw the planet here like this, right? So you got a probe here like this, right? What is the KE of the launch? Launch KE is what? No, it's just like, I mean, launch K is half m, then half m times half v escape square, right? That's the launch speed, right? Okay, then they're asking what's the maximum height, like, where would it go, right? So what's the Ke up there? 0, right? Like that would be the point whereby it becomes 0, right? Okay, right, at a certain distance, right? Okay, so what do they want? They want the height, right? They want h, right? They want h. But then there's the r to consider. There's the radius of the planet, right? The r to consider, right? Like this. Okay, now the Ke has been converted into what? GPE, right? Always remember. Most of you, I've seen the working that you sent me this question for. I think at least 2 or 3 of you asked me this question from this paper as well, right? Which is why I'm going through this now. Always remember. Hey, look up. I start from now. There is GPE here. There is also GPE there. You need to find the difference of the GPE. Most of you, what you just did was you just converted the KE into the GPE, thinking that that's the amount of GPE that will get up there. It's not. The KE will help it to change the GPE from here to there. So the KE that you give it, right, the KE of the launch, right, will be equals to GPE final minus GPE initial. So what is the GPE final? So it will be negative GMM over R plus H. Then you minus negative GMM over R. And that's what a lot of students are missing. That part there. Right? Which is why I sent it out in the group chat saying, please remember. And do this for electric potential as well. Do this for electric fields as well. If you got 2 plates, right, and your particle has some Ke here, as the particle goes over there, the Ke is converted into EPE, right? EPE. Always remember to check what's the initial EPE here, what's the final EPE there. Always remember to check the difference of the EPE, right? Not just convert Ke into GP. This is no longer secondary tree science, right? This is no longer like, whatever Jamestown is putting you through. Okay, there you go. How do you know Yaphan? Yaphan is also a few years older than you, right? Oh, because it was a 4-year thing, right? So when he was a year 6, you guys were year 3 or something like that, right? Okay, yeah. No, Yaphan's cousin was one of the first few students I taught from the ACSIB, and he came to visit just now. Yeah. Is he not in BB? He's in BB, right? Oh, so he wasn't BB in year 3 and 4 lah. What were you in year 3 and 4? Waste time. Okay, come. Alright, so do you understand? Huh? You did that, but then you still got the wrong answer. No, it must be like negative this minus that, no? Yeah, lah, so your working sucks lah.
I think my math sucks.
Yeah lah. Okay, I mean, short of saying that your math sucks lah, but okay, your math sucks. I can't help with that, dude. And the worst thing is that his name sounds like math. Yeah. Problem for later tonight. Yeah, it's not my problem. It's not my problem. You have to go and figure it out. Okay, alright. D. Does anybody need D? Huh? Okay, I don't quite understand what the context is, but yeah. That's that. Oh, right. No, having wanting and needing is different thing, right? You might want it, but I don't know whether you need it. Okay. D here. Please take a look at this, right? Gravitational potential. right? They show you the potential at some distances from the surface, right? They ask you some trick ass question. They ask you what's the gravitational acceleration. Look at that, right? Look at that. Look at that. What gravitational acceleration? Are you gonna get tricked? No, you're not gonna get tricked. What is the equivalent of asking you to find the gravitational acceleration? Asking you to find the field strength, right? They want you to find the G field strength. So we write down the G field strength here. Okay, G field strength. But here's the thing, G field strength, but they give you what? Potential values. Come on.
The gradient.
Yeah lah.
Yeah, the gradient.
The gradient lah, right? But how are you going to find the gradient? They ask you for the G field strength at 230 km. How are you going to find the gradient? So what the most mistakes that students make for this question here is they take the potential value here and they divide it by the distance here. Absolutely wrong, right? Okay, you know what happens when you do that? Right, the planet here, right? The distance here, right? Some more distance from the surface. These guys are tricky, right? Distance from the surface. Look at that. Okay, so from here to here, look at that. This is the distance, the height here, like this. Then if you take this value, you divide by this value here. This is the potential here, right? This is the VG here. What you're doing is you're taking the potential amount and you're dividing it by the distance here, right? Which is wrong, right? You're supposed to okay. I mean, if you plot all these onto a graph, right? All these values, if you plot it on the graph, how does the graph look like, guys? VGR. How does the graph look like? What the? All right. On the surface of the planet is the most negative, dude. Right? As you go further away, it becomes less negative. The potential increases, but it's less negative. Right? So what are you supposed to do when you're trying to find the potential gradient, like at a point? What are you supposed to do? Draw a tangent, is a tangent this thing, right? And then find the gradient here, right? Okay. So does it make sense for you to take the potential value here and then divide it by the distance there? No, right? Okay, so what you're supposed to do is you're supposed to take the value before the value you're finding, right? And then you find the change across. You find the change across. This will be the dr, and this will be the dv, right? So you find the difference between the two values above and below, right? And the two distances above and below, and you find the change. That's the answer. Interesting. What? What? Yeah, but here's the thing. Okay, guys, I can't spend too much time on this. You know why? It's not likely gonna come out. It's not likely gonna come out, right? Yeah, and even if it does, maybe it comes out in a different form, like a graph. Not like that, right? As much as I want to shit on them, right? They are not that stupid. Okay, right? Yeah, really. Okay, so they do have some sense of like trying to mix things up, right? Which is good. All right. Am I done with 23 prelims? 23 prelims. Who else wants to ask what's next? No, nada. No, no. Anyone wants to ask prelim questions? Those online. I give you like what? I have until my next class until my next class is 3:30 though. Is it 3:30 my next class? My next class is 3:30 I think. What? Next class is the next class 3:30 is the year 4 IP. Year 4 IP. Bunch of slackers though. Huh? You guys are not as slack, is it?
Wow, that's great.
Yeah.
So
Yeah.
the voice 40 minutes to 90. Actually, our force.
They are a bunch of slackers, but they are the ones who are the top 10 in the level.
That's a difference.
Yeah, super annoying though. Yeah. Okay, right. Prelims, those online. Anyone, any other prelims? Like now, come on. Oi.
Because
21 prelim. Okay, 2021. Right. Yeah, why not? Okay, come. Since he asked for it, so I'll give it, right?
No, what was the guy? What's the goal? It's a guy. What?
2021 there was no paper 3, so be very careful when you start when you do this. 1B. Oh, okay. Determine the speed of the sphere 1.2 seconds after release. Is that right? Is this the question? Yan Yu, this is the one, Okay, okay, hang on, So we are supposed to look at this diagram here, and we are supposed to determine the speed of the sphere 1.2 seconds after release, right? Speed of the sphere 1.2 seconds after release. Okay, let's look at this,
They're both linear, and they both
Holy shit! What? What? No, this is paper 2. No, this paper 2. This is kinematics. They were very well aware that there was no paper 3 in this year. They knew there was no paper 3 in this year. Oh wow. Ticker tape timer? I don't know. But hang on. Have you found the first one? Acceleration of free fall? Have you found it already? You found it already? What is the value for this one? Yeah, how much? I think I need that value. 9.7. Okay, so 9.7 meters per second square. That's acceleration of free fall. All right. So that's 9.7. Right. They did say that these pictures were taken at 0.1 seconds intervals. Right. So what you will have to do is to use the vertical distance values, right, to help you determine what's the acceleration of free fall. Hang on, I would have to use S equals to UT plus half AT square. Yeah, I would use this because it's very convenient. Since it was released from rare, I mean it's projected horizontally, so the vertical speed can be taken as 0 as well. At the start. So I would take S is equals to half GT squared. Right? You get that? So what I can do is I can just go and take the last data point here, right? Did you take the last data point, Yan Yu? I'm talking about part A, Yan Yu. 1.75, all right, 1.75 here. Right, so then I'll put 1.75 equals to half G. Okay, so now the T, the T squared, all right. So I think, like, there's a reason why I want to go through this. How much time has passed from the start until it fallen for 1.75 meters vertically? 0.6 seconds. 1, 2, 3, 4, 5, 6. All right, so 6 spaces. Count the spaces. So 0.6 seconds. Yeah, I think you can get your G here nicely, right? Okay. All right. But back to his actual question. His actual question was part B. Determine the speed of the sphere 1.2 seconds after release. Determine the speed of the sphere 1.2 seconds after release. But the problem here is that this is only up to 0.6 seconds. Right? You can only, like this, right? Yeah. So we can't use this graph anymore. No, you can't. No extrapolate. What? Extrapolate to the next page, bro. Okay. No. So here's the problem, right? We want the speed, which is a bit strange as well, right? I mean, why didn't they ask for velocity, right? So which means that they want the magnitude, but they don't need the direction. Right? Because if they had asked you for determine the velocity of the sphere 1.2 seconds after, you have to give the velocity, you have to give the direction, but they only wanted the speed, right? So what does the sphere have, right, at 1.2 seconds? Would it have a very big vertical speed? Yeah, it will have, right? Does it still have its original horizontal speed? Also have, right? Yeah, like this, right? So what's gonna happen then? What do you think you need to find? Yeah, you need to find the resultant, all right? So you need to find out what's the speed of the vertical 1.2 seconds later. So you can use what? You can use v squared equals to 0 plus 2g. No, this is s, right? Sorry. Wrong one. I don't even know what's the distance. I can't use this one. Anyway, just v equals to u plus at lah. Right, so v equals to u plus at, right? 0 plus a, which is 9.7, right? What we found just now, 9.7, and t is what, 1.2 seconds, right? Yeah. So we can find the v, right? We can find the vy. What's the vy, guys? 11.64. 11.64 meters per second. That's the first answer. How about vx though? So for vx, you have to find the graph again. You have to go back to the graph again. So you need to find out what's the horizontal speed. I would expect it to be a constant horizontal speed, right? Which it should be. So you have to check, right? I think it does look quite constant now. Okay. So yeah, that looks quite constant enough. So you know what? I can just take one reading. So the Vx is equal to what? What's this distance here? 0.3 sounds right. Because the middle will be 0.25, right? 0.25. And then let's say there are 5 grid squares. This looks like the second grid square. So what? So it's at 2 over 5 times 0.25, right? 2 over 5 times 0.25. 2 over 5 times 0.25. Then plus 0.25. Actually, 0.35. I would use 0.35. 0.35 divided by 0.1. Right? Because they say the interval time, right? This time interval here between two dots is 0.1. So divided by, so it's 3.5 meters per second, right? 3.5 meters per second, right? Okay, then the Vx here, right, will be equals to 3.5 meters per second, right? Then what do? How do you find the resultant speed? Yeah, Pythagoras the thing, right? Pythagoras the thing. So you find the resultant from here. This will be the Pythagoras, right? 3.5 squared plus 11.64 squared, then square root. That will be your final answer. Okay, Bob? What? Yeah, I think there will be a range lah, right? Anyway, 4 marks, so you can get quite a lot here. No, if it's velocity, right, you have to find this and then find the angle. If let's say this one is velocity, right, make sure that you go and find the angle. Yeah, that's right. So you can, I mean, you have to use tangent or use cosine or whatever it is. Yeah. Okay, good. Anything else? Prelims, ACS prelims? Question 3B part 2 from the same paper, 2021. 3B part 2. Show that the change of momentum of the bullet as the bullet travels along the length of the barrel is approximately, I hate this kind of word, approximately 9 Newton second. Show that the change in momentum of the bullet as it travels along the barrel is approximately 9 Newton seconds. This is a what graph? What graph is this? This is a force time graph. You have to count squares. You have to count squares. Right, look at this question. It says approximately 9 Newton seconds. Change momentum of the bullet as the bullet travels along the length of the barrel. Right? It showed this one here is force on the bullet against time. So you got to count squares. Oh gosh. How are you gonna do this? Okay, what's one of the styles? The styles is if it's more than half of the grid square, you count it. If it's less, you don't count it. Yeah, so you work backwards, you work backwards, right? You go and find the area of one square, right? Based on the force and the time, right? Then you say that each square area is this much. Then since they ask you to show is 9 Newton seconds, right? You work backwards and then you just say that
like that, you put here this one, you put here this
No. So what you do is in your answer, right? In your answer, you work backwards, right? Your 9 Newton seconds, right? Then you work backwards in your. Then you say that, oh, I have counted 31 squares, from the graph, like that.
because like
And then afterwards, then you say, it's like, then multiply by the area of each square equals to 9 Newton seconds. Hashtag shown. Hashtag, right? No. Huh? Okay, what are the other ways of doing this? You can go and take this triangle here lah. Right? You can go and get the triangle there. Oh gosh, my hands are like not steady. Huh? Yeah, lor, correct lor. So you break it up lah. Yeah, like that, bro. Oh man. Hey, not me lah. Don't kill the messenger, man. Right. Yeah, there you go. Oh, 连名带姓. Yeah. Right, so that'll be how our, like, that's the other way of estimating it lah. Right? Huh? Li Feng. Yes. Okay, so just take note of that. I mean, whichever way you want lah. Okay? Right. But I mean that other way is quite funny, right? The other way is like, oh, I've counted 31 squares, Then the teacher will be like, shit, do I mark you correct or wrong? Like, no choice, right? You put him in a position, right? What? Exactly, right? So yeah, you just put it there. Yeah. Okay, anything else from the 2021 prelims? 2021 prelims. Whoa, use Newton's law. Explain why a gun will recoil when a bullet is fired. Huh? Yeah, action reaction pair, right? So the force by the gun on the bullet is equal and opposite to the force by the bullet on the gun, right? But I think you still have to quote the momentum part. So you still have to say that the momentum of the bullet is equal to the opposite momentum of the gun, and therefore the gun will recoil. Yeah. Yeah. Anything here? I think it should be okay. Standing waves though. Standing waves. No standing waves, is it? No. All right. Watch out for standing waves in your paper too. Okay. Watch out for standing waves. Watch out for the gravitational thing in the gravitational, right? The GPE thing, the change in your paper two. Watch out for standing waves in paper two. Yeah. 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 This was damn freaking annoying. This one. Yeah. This one's damn annoying. So each one is 0.75, right? So in series they add up. So it's 0.75 times 4, which is how much? 3 volts, right? This is 3 volts in parallel, 3 volts in parallel, 3 volts in parallel. The total voltage out is only 3 volts, right? Then the total resistance will be 1.8, 1.8, 1.8, 1.8 in series, then parallel, parallel, parallel. Then you can find the total. Yeah, then you just simplify to one solar cell, right? One big solar cell. Oh, one more thing, guys. Solar cell. What's a solar cell? No, solar cell is the thing that gives you the electricity, like this solar cell on my calculator. That's a solar cell. Solar radiation convert to electricity. Solar panel is just a piece of glass with hot water pipes behind, with black water pipes behind. Yeah, that's pretty much it, right? Huh? What? To absorb the heat, dude. Must make it into an issue for everything that you do, right? So these are all cells, right? These are all cells. Hey, didn't you hear what our new prime minister says? Hypersensitivity is not an answer. No, like, wasn't it just? Yeah, so this is a solar panel. There's a solar panel. So it absorbs solar radiation, right? Right. And then there's a water pipe, right? And all you get is just hot water. Yeah, right? You can't get electricity from a solar panel. According to the IB syllabus, a solar panel is this: water, right? And the photovoltaic cell is your solar cell. This. Okay? All right, good. Anything else on 2021? Calling once, calling twice. All right, and we are sold. All right, IB papers. IB past year papers. All right, bring it. Which ones you want me to go through first?
Sometimes you got 38 for
38
8, 20, 23
MCQ paper.
No.
You got 38 for MCQ? No, you got 38 for paper 2? The heck?
It's all about
What? Okay, which year? Come on, call it. What's that? May 23. May 23. Okay, good year to choose from because it's a bit obscure. What's that? Time zone 1, paper 2. Question 5B part 2. Let's look for 5B part 2. 5B. May time zone 1. Okay, I'm gonna write this down on the group chat here. This is what? May 2023. Alright. Time zone 1, paper 2. Right? I mean, that's just the paper that I'm going through now. Right now. Question what? 5B. 5B part 2. So this is 5. Hang on, wait, hang on, no, hang on, right, wait, this just came in the other day only, and these buggers were really damn tricky about it. Tricky. No, wait, what does? Are you sensitive to that word? Like they're really a bit tricky about this. Okay, listen up, So side quest here, okay, side quest here, right? So this is my, I'm not predicting anything. I'm just saying that just be aware if they try to trick you on this, okay? All right, I'm gonna ask you this, okay? Hang on, I have to think about this first. Okay. Okay. What does this represent? This is in mass, right? This is using the representing mass in terms of the unified atomic mass, right? Okay. 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 Wait. Look through your data booklet. Okay, I'm gonna shut this because I need the space. Look through your data booklet. Okay, I'm gonna zoom in as well because I want to cut out all the distractions. Okay, can you tell me what's 1U? Oh, that's thick, man. That's thick. All right. What's 1U? What do you get for 1U? Okay, so for in kg is what? Yeah, give it to me in kg. 1.661 times 10 to the power minus 27 kg, right? Okay, kg, right. Now, but there's another version of this unit. There's another version because you see, right? I have not seen this in a long time, and it just surfaced just a couple of days ago only. All right. What is it in MeV? What's that? 931.5, right? 931.5. Okay. Now, what does these two numbers mean? What's that? What's 1U? Is it one atomic? Okay. Conversion is correct, right? So if you convert this mass into pure energy, if you convert this mass into pure energy, right? Okay, this is the amount of energy that you get. You understand what I'm saying? But that also means that if they give you this unit like this, right? If let's say they tell you that one unified atomic mass unit, right, is 931.5 MeV slash C minus 2, right? This is actually showing you the amount of mass that it has, but in terms of energy units. You get how confusing that sounds, right? So it's like if let's say for example I want to present to you the like the mass of something, okay? I can do it in a few ways. I can present it to you in the terms of U, right? Let's say for example deuterium 2.0141 U, right? I can also present it to you in kg, Like I may want to present it in kg. Let's say I don't present it this way. I present it in kg. It will be what? 2.0141 times 1.661 times 10 to the power minus 27 kg. Correct? I can present it the mass of this deuterium in this format here like this. Correct? I can also, if I choose to, present it in the form of that other unit, the MeV slash C minus 2. It looks hella confusing, but this is just mass. This is just mass. Okay? This is just mass. But the mass unit is a bit different. Like what is the mass unit of like equivalent? Since it is 2.0141 U, right? If I want to present it in these units, then it will be 2.0141 times 931.5. Because 1 U is this amount of energy, right? You understand this? Please do not confuse this with binding energy. This is not binding energy. This is kind of like total energy, right? When you convert the mass into energy. Like this is just mass in another unit. Right? So like I think we rarely have done any examples like this before. Yeah. Not even in any of the IB paper, not even in any of your prelim papers. So it just came out one day because one of the students showed me this question, right? And then I was like, oh shit, yeah, this is what they can do too. They can also give you the mass in these units, and it becomes very confusing for you to how to deal with this thing here. Right? It becomes quite confusing, huh? All right. So let me just show it to you. Hang on. Let me show you how to deal with it. Let me just show you how to deal with it. Hang on. Like that. Yeah, it was like this. You see, calculate the energy release in joules when the fusion reaction happens. So the fusion is deuterium, tritium, giving you helium and one neutron. Okay, and they gave you all the masses. Oh shoot, those are who are online probably can't see. Sorry. Okay, and they gave you all the masses in MeV slash C minus C to C to the 2. All right. Yeah, like that. Okay, and the working, like everyone's like a bit messy about this working here. Okay, no, sorry, that was the fusion reaction up there. Okay, how do you do this? How do you use this information? How do you use this information? This is not binding energy. This is not binding energy. This is mass in another units. What? So what you can do really is just, yeah, since you know it's mass, right? Since you know it's fusion and this one produces energy, right? I believe it produces energy, hydrogen to helium, right? Anyway, the number there is wrong. It's not 4-1. Sorry, there's a mistake there. Yeah, it's 4-2. Right? Okay. Sorry, let me just copy and paste this onto my PowerPoint first. Right, let's solve it. Let's solve it here. Hang on. Right. So I'm just trying to help you lah. Okay. So you want to find the total mass here, right? You want to find the total mass here and the total mass there, right? Total mass. Okay. Total mass here and the total mass there. So don't get too confused about this thing. Just remember that these numbers, right? MEV slash C to the power 2 is just mass, right? In a different unit, right? We'll deal with that later. Find the difference now. You got some calculator, right? You can find the difference. Yeah. Why? You all go LinkedIn and bring calculator. Okay. Count the number of words. Yeah. How you go to exam never bring glasses? What the hell, dude? Hmm? 1.7. Is that right? So the difference in mass, right, is 17 MeV slash C squared. Right. But you need to calculate the energy released. It is just 17, no? It's just 17. But you see, oh yeah, yeah, I'm just saying that, you know, if you have the mass defect in this, then the energy released is 17 itself. Okay? This is not binding energy. This is you converting everything from mass to energy already, and you already have done the job, right? You already done the job. You find the difference in mass in these units, you are actually finding the difference in energy in the MeV units itself. Okay? Right? Because we know that del E equals to del M C squared, right? So, that's why the del E is just these units here, right? Don't go and multiply by the speed of light or anything like that, right? You get it wrong, right? I mean, the C squared takes care of itself already. So it's just 17 MeV, that's it. Okay? Right. Then you can finally say that the energy in joules, right? I think you know how to do this. So just 17 times 10 to the power, or 1.6 times 10 to the power minus 19, right? Times 10 to the power 6. Okay? So that will be the conversion to joules. Right? So just in case, just in case. Right. Then there are other questions where they give you the binding energy per nucleon. Don't forget about those kind of questions as well, right? So you have to go and check the binding energy. And already went through in the CTs recently already, so I don't think they'll give it to you. Yeah, I don't think they'll do a, like, I think the guy probably embarrassed already, right? No, like he probably don't want to set the paper for now already. Okay? I don't know. I don't know whether he'll be embarrassed. I would. Okay, but back to your actual question. Sorry, Veer. Right? What is this they're asking for? This one here, show the energy release. Huh? The second part of this one. So this one here, is it the same? Oh, hot damn! It's the same. It's the exact same one. Yeah. No, it's just in a different unit. Yeah, just in a different unit. Wow. Okay, that's strange. Okay. Did I just call it? Okay, never mind. We'll see. All right. Stranger Things. Okay. They ask you estimate the specific energy. So you got to remember what specific energy stands for. And unfortunately, that's in topic A. It's energy per unit mass. Yeah, yeah, energy per unit mass, right? So basically, you have to go and calculate like the total mass is 1 kilogram, right? The total mass is 1 kilogram. But then you have to go and calculate how many fusion reactions happen. Yeah, that's the more concept part. I'm sorry, guys.
So 10 is not good enough.
To do more concept.
Yes. Okay.
Come on, guys. But I think the mass is in the correct ratio. It's 0.4 is hydrogen 2, 0.6 is hydrogen 3. I think the ratio is correct. Huh?
Oh.
Yeah, yeah. I mean, it's just like 2:3, right? It says 2:3, right? 4:6, 2:3. Okay. So your job is to just find, okay, you know that each fusion reaction, every time one deuterium fuses with one tritium, you're gonna get 18 mega electron volts, right? So you just focus on trying to find how many, particles there are in these masses here. I think you can just use one of them, because if you find the number of particles for one of them, it will be the same ratio. So you don't have to find both. Yeah, you just take the 0.4. Yeah, but yeah, I know. So how do you do this then? So you need the mass of one deuterium. Oh, they gave, right? Yeah, they gave. Yeah. So 0.400 kg divided by 2.00141 times 1.661 times 10 to the power of minus 27. This is in kg, right? This is in kg too, right? Yeah, okay, that's fine. No need. No need. No, you don't need to, because this is the mass of one hydrogen particle, right? And this is the total mass of the whole collection of them, right? So you just divide this. This will give you the total number. You don't have to go and multiply the Avogadro's number. Yeah, yeah. Do it. 1.2. Can I get more decimal? 1.195. Okay, 1.195, because it's a, I think it's an intermediary. Yeah, it's an intermediary. 1.195 times 10 to the power of 26, right? Particles, right? So that's the number of fusions that you will get, right? If you try to do this for this one, I think you'll get the same number as well. You get 1.1952, right? So yeah, it's a bit strange, but yeah, right? But go ahead and just use this value here, all right? And then you should be able to get the, like, so this number, right, times 18 mega electron volts, right? This is the total amount of energy, however, in mega electron volts, right? This will be like the total in mega electron volts. The problem is, if you are specifically asking me for specific energy, I would believe the answer, the unit should be joules per kg. Yeah. Yeah, so this one divided by 1, but you will get MeV per kg, right? So it's very likely that specific energy being like, a quantity that you need to be very specific about, right? So you have to do it in joules per kg. I believe so, I believe so. I don't know whether the answer key gives it in MeV per kg, but I would just change it to joules per kg, like me being me. Okay? Yeah, let's stop. Yeah, it's right there somewhere. What? What question again? 5, 5B part 2, is it? Yeah, they actually have to do joules per kg, man.
But I mean, if I did,
Allow, for marking point 2, right? Okay. Right, so fine. Yeah. What? What?
wait, why got one there?
Yeah, both methods okay. Yeah. Don't worry. Yeah, if your more concept is not that great, right? Just stick to one method. Yeah, fine. Yeah, just stick to that one method that you know. Like, just do that one method. Yeah. Okay. This one though interesting, because I think I haven't seen this in a while. So what's the problem of like, energy production by nuclear fusion? So do you understand that we can actually do fusion very easily in the lab? Yeah, it's just not like, it's not a sustained reaction, right? Okay, it's not a chain reaction like fission. Okay, so the two difficulty is what? Trying to reach the high temperature and trying to reach the high pressure required. It's basically high temperature and high pressure. Really? No lah. Okay lah, so requires high temperature and difficult contain lah. Okay lah, yeah. That's a bit strange, but okay. Huh? Okay, what's the next one? Any other requests? Come on. Paper 2 tomorrow. All I can do is just go through the things that you have done so far. Go home, play econs. Go and sleep is a good idea too. Yeah, you got 2 papers tomorrow, man.
If I don't sleep tonight, I don't know what's I'll read the questions wrong, and a few questions I come up with, I'll get it. So you need to like
Huh, what?
Like, oh, I did so bad, then he lost like 3 marks.
Shut up lah.
Yesterday when you said I did so bad, right, I knew you were gonna say I lost like 4 marks. Hey, shut up, like.
No, I got request. Whoa, whoa, whoa. Sorry, I got request coming in. May 2018. Like, let's go to May 2018 first, right? First come first serve. Sorry, May 2018. Oh, you can edit messages. Oh, I didn't know that. May 2018. Time zone 2. May 2018. Time zone 2. Paper 2. May 2018. Time zone 2. Paper 2. I keep thinking of like I'm missing something though. I keep like this weird nagging feeling telling me that I have to say something, but I just keep not remembering what I need to say. I don't know, man. Yeah, but anyway, you guys look at this one here. This one here is the potential meter, right? Yeah, this is the potential meter. Yeah, right. They just don't call it potential meter. So the way I teach it to you, right, is like it's just something that will come out. Nobody wants 5? May 2018 question 5? I mean, this was one of the more interesting ones that came out in recent years. 5? This one here? What's happening here, guys? I mean, the answer is just a straight line though. But why? You got two sources, right? You got two lamps here, two sources, right? I mean, what were you expecting the screen to show? You were expecting to see the screen to show a pattern, right? Two sources, two source interference pattern, bruh. But it's not. No, no, no. I mean, even if I put two slits in front of them, right? So what? What's happening here? Yeah, incoherent sources, right? So two light bulbs are always incoherent. Yeah, so not just for yeah, bulbs are always incoherent, right? So what happens to the intensity? What happens to the intensity graph here that you see? It's straight, right? But at how much? At 2, right? Because they don't overlap, right, long enough to give you that bright fringe, right? So you don't get the 4 times the intensity. Do you realize that if it's like one bulb, right, with two slits, and each one is I naught and each one is I naught, then at the center, what's your bright fringe intensity? 4 times the I naught. Right, you know this, right? So it doesn't become 4 because there's no interference, right? Because it's incoherent. So if it's incoherent, it's just overlapping of two light bulbs. So that's why it's only 2, and it's a straight line like that. Okay? All right, good. All right, sorry, Arit, let's go back to your question. Um, oh, he asked for 4C. So it's somewhere around here. No, 4C. He asked for 4C. It will not have constructive interference. The rule still applies. The rule still applies. It's just that because they are incoherent, you cannot add their amplitudes anymore. Because the reason why it becomes 4 times the I naught here, right, is because each of the amplitude A naught and A naught, right, when they interfere at the central fringe, it becomes 2 times the amplitude. And with 2 times the amplitude, it becomes 4 times the intensity, right? Alright. Yeah, but then for this one here is the amplitudes are not interfering, right? Because they are two, like, separate sources. You get? Yeah, it's random, so therefore they don't interfere. They're not coherent, they're incoherent, right? So the, huh? What? That's one light bulb. That's one light bulb with two slits. It's coming from the same source. This is two lamps. You get it, right? This one's only one light bulb only. So like from each of them, right? The both slits here are coherent. These two are incoherent. So incoherent will not give you the pattern, and incoherent will not give you the interference. So you only get like 2 times the intensity here. Okay, okay. Sorry, Arid, 4C is it, Arid? Okay, what is it? Cell X is replaced by a second cell of identical E, but with internal resistance 2. Comment on the length in which the second cell is 0. Okay, so this is pretty much like the thing that I've done, right? It's just that it was rotated halfway. So you know what? I'm gonna rotate it this way now, right? Just to make it look like the way we did it. All right. Okay, Arid. Right? Do you see that this is your galvanometer? Arid. Okay. What's the objective of the galvanometer in a potentiometer? If you recall the lesson that I went through, what's the objective of it? I mean, yeah, I mean, you basically slide the jockey side to side until the galvanometer gives you what? Zero reading, 0 ampere reading, right? The objective of the galvanometer is to give you what again, Arid? 0 ampere reading, right? But why does it give you 0? Like why is it? Yes, the voltage across A to C is the same as the voltage across the EMF here. Like, let's say for example this is 6 volts and this one here is 6 volts. You get what I mean? So in the question that you asked for C, they're saying that they're going to use another new cell of the same EMF, but then the internal resistance is like 2 times. Right? Isn't that what they said? Okay, now there's internal resistance, right? Okay, so from no internal resistance to internal resistance. Okay, yeah, right. So, okay, do you understand if I tell you that the internal resistance, we don't give a hoot about this? Like, we don't care. Like, but why don't we care? Why don't? Because when it's balanced, there's no current. When there's no current, the internal resistance doesn't take up any voltage. So the length is still the same as before. If your EMF here is 6 volts and the balance length is still for the 6 volts here, right? Then having internal resistance in this cell or not doesn't matter because the galvanometer is 0 amperes. Didn't I do a more advanced example on this one where I gave you a circuit, right? I gave you a circuit and I showed you how to connect it, right? So the point is, if it's just the cell alone, if you're just right using the potentiometer to test the cell alone, right? The galvanometer, you all you have to do is just make sure that the reading of the galvanometer is 0 amperes, like all the time, right? 0 amperes, right? Because that would mean that there's no current flowing in this circuit, right? In this cell. If there's no current flowing in this cell, then there's no voltage given to this internal resistance. Then the 6 volts balance the 6 volts, right? The EMF will still be the same, right? The balance length will still be the same, okay? Yeah, right. So that's for that one there, right? That 4C there, this one here. Okay. Then you got a request for 6C, is it? 6C. All right. What? Okay, so they want you to estimate when the asteroid was far away, the planet had away from the planet, it had negligible speed. They want you to estimate the speed as define a point B like this here, right? Am I right? This point here, they want you to find the speed. Is that right? Okay. All right. So when the asteroid was far away, what do we understand about the asteroid being far away? This is the asteroid, right? And infinity. So what does that mean? What? The GPE is 0, right? the KE is also 0. Okay, so the idea here is now the asteroid has moved all the way to this point here like this, right? The asteroid went from infinity, right, at infinity, all the way to this point here, right? Okay, so what kind of question is this? This is just KE GP, right? Right, the KE gain here, right? The KE gain here is basically the amount of GP that it lost, right, going from infinity to this point, right? But the good thing is you don't have to really care about the final and initial, right? Like what I just did the example earlier on. This one here is just what? The initial is 0. So all you have to do is just find the amount of GP here. So I would believe that this is GMM over, right, R plus H. I do believe that you have to make sure that you get the correct, right, values here. So this is like H and this is like R. Okay? So they did say that radius of the planet is this, at point P a distance of this above the surface of the planet, right? Yeah. Hang on, hang on, huh? We don't have to care about the negative sign because I just want the value of it. Yeah, you're right. I mean, it is negative, right? There is a negative sign, right? But I mean, it's basically this. I mean, the loss of GPE is equal to the KE gain, right? So I just want the magnitude of it, right? Okay. But the problem here is this: they didn't give you much information other than from this. They tell you the G field strength is 2.2. They tell you the G field strength is 2.2. That don't help much. Does it help much? Right? I mean, if you wanted, yeah, if you wanted the okay. So let's say okay, they wanted what, the speed, right? They wanted speed. That means you have to have half mv squared equals to gmm over r plus h. You can cancel out the small m. You can cancel out the small m, right? And you can find the v, right? But you don't have the big M of the planet, right? But they give you the G field strength. So we gotta have to learn how to use this. So how do I use the G field strength here? So it's Gm over R plus H squared, right? Equals to 2.2. Okay? Right. But do you have R plus H? Yeah, you have. You can actually go and find it. Right? You can find the R and the H, right? And you can find the GM, and you can sub the GM into this. You can find the V for sure. I guarantee you. Right? If you don't want to go around playing around with the units and all that, you just find step by step. Nobody's gonna fault you for that, you know? Right? Shortcuts are only useful when you already know the long way around. Right? Wait, hang on. What? Sorry? Uh, really? You calculated the previous part? Oh, sorry. They already asked you to find the potential at point P? Yeah, sure, go ahead, yeah. There you go. That is the potential at point P, Gm over R plus H. Yeah. So this thing here is the part B's answer. Sorry, I totally didn't realize that. That's the part B's answer, like on its own, on its whole. Gm over R plus H, right? That's part B answer. Yeah. Yeah, but which is half V squared though. Half V squared. Then you make V the subject. Okay? Alright. Done? Okay, this one done. 9A. Let's go to 9. 9. 9. Yeah. What's no. Da is Russian, yes, right? Yes. Then what's German, yes? Yeah. Yeah? Yeah. 9. Yeah. 9A. 9A. Oi, what is this? Rutherford constructed model of atom based on results of alpha. Describe the model. Oi, what are you asking this for, dude? Are you asking me what's in my notes? Oi, part B. Okay, all right. So this one here will be different. Okay, Bohr modified the Rutherford model by introducing this condition, right? Okay, so what is this nonsense here? What? What is this thingamajig here? Yeah, like what's MVR, guys? Okay, this is the only quantity that is not in syllabus. Yeah, the formula is there. But this is the only quantity in topic, I mean, in the whole syllabus that is not in syllabus. That means you're not really tested on this. All right, but you still need to know what's the name of mv times r. It's called angular momentum. Yeah, it's called angular momentum. All right. Okay. 12. Yeah, and if you read the notes, what Bohr did, right, which was a bit no theoretical justification. If you remember in my notes, I did state that he assumed the angular momentum to be quantized like this, right? That means the you know h and 2 pi are constant, so you just need to multiply by n. So he assumed that the angular momentum for different electrons is quantized, right? But there was no theoretical justification behind this, right? Why? Because it's not like you can measure the angular momentum of an electron anyway, right? He can only what he did was he only predicted that it was going to be like that. Yeah. Okay. All right. Other than from that, I don't know how to answer this question. Yeah, I mean that's all I can give you, right? Yeah, that's all I can. That's all I know. I know if you ask me every year, right? If I were to sit down to this question, I mean I can memorize the answer key and tell you the answer key, lah, right? But in my own context of me learning the syllabus and all that, I would not have been able to get the full 3 marks here. Yeah, I mean I'll just be frank with you, right? I mean I go through this paper how many times already? Like 6 times. I just cannot remember the answer key, right? And I don't think it was important enough for you to go and memorize it. But there we go. Let's check the answers. Right? That was question 9, is it? 9B. Oh, where's 9?
Sorry.
It's gonna be another kilometer. Kind of fortunate. I'll do the percent. I'll do a percent. That's not here in front of me. You're going to watch it. Sorry, Mr. Leong.
I don't want to.
I apologize. Oh, it's a bit complicated.
Oh, okay. Right.
We were incompetent regarding physics. In physics now regarding
That's the answer. Yeah, that's the answer. Yeah, that's the answer. Huh? No, you have. I use this reasoning for Schrodinger's. Okay, what's Schrodinger's model? What did he assume the electron to be? Yeah, I know it's cat one. Schrodinger's model, what did he assume the electron to be? No, a wave. Right, a standing wave. Right. Why did he assume that it was a standing wave? Why did Schrodinger assume that the electron was a standing wave? But why? Why specifically a standing wave? Because as the electron is orbiting around the nucleus, it's not transferring energy, right? So that means the energy is still kept within the electron orbit, right? That was what I mentioned about it, right? So that's what I stated. So for the Schrodinger's model, similar to the Bohr's model, is that the electron doesn't lose energy, because if it did, what will happen to the electron? What happens to the electron if it loses energy as it travels? What happened? It will crash into the nucleus, right? Yeah, and if it crashes into the nucleus, what happens? Then you get proton electron capture, right? So as the electron goes in, right? Correct. So the idea here is, does it? No. On a daily basis, you look at all the atoms around us, it doesn't. So what's the inference? You infer that the electron doesn't lose energy, right? That was a similar model that Bohr and Schrodinger had. But Bohr treated the electron like a particle, while Schrodinger treated the electron like a wave, right? That was the big difference between the two of them, right? But their underlying concepts are the same, right? And the electron doesn't lose energy, right? Okay, 7 and 12 I haven't revised yet, I know, right? 7 and 12 I haven't revised yet, but this is very obscure. This is a very obscure question, all right? So these 3 marks here, skip lah.
Like the rest of them.
Right? I mean, I'll be happy if you get 87.90, right? I mean, sure, no problem. Oh shit.
I think 50 now.
Okay. Yeah, yeah. I mean, yeah, like, this is not easy, right? Honestly, I mean, I tell this to everyone year to year, right? I rarely play that kind of like, oh, you just study this and then you can more or less get 70% and then just like, do with it, right? But what if the entire question is very heavy on some topics, right? So this is one of those that I say, like, I myself I will let go of. Yeah, right. It's not something that I can do it. I can get it right myself. Yeah, right. Yeah, unless I go and, I don't know, go and study theoretical physics. I'm not gonna do that. All right. So that's all I can offer you for 9B. Okay,
Just give up.
Isabel. Hang on, easy. November 2016. November 2016. There's no time zone, but okay. Paper two. Question 5C part 2. Oh, that sounds really specific. Question 5C part 2. 5C part 2. What? Yeah, sure. Yeah. I told you already, just gonna reuse some of these questions, right? Okay. Calculate the minimum time between the wave leaving the transmitting antenna and its reception. Oh, damn. Okay. Sorry. Isabel, this question here is a very silly question. You just basically need to know the distance between the two of them, right? Like the distance between them, right? The distance here, and then the speed of a EM wave, right? Is a EM signal, right? So the speed of an EM signal is 3 times 10 to the power of 8, right? Meters per second. So all you have to do is just take this distance, right? What's it? Distance, speed equals to distance over time. Time equals to distance over speed. Take this distance divided by the speed. That's the time taken for the thing to receive. Do you have the distance? Did you calculate the distance previously as well? Yeah, okay, yeah. So yeah, you find the distance. So yeah, it's a bit strange, right? Like, yeah, but it's basically just playing around with the EM wave speed. Then got the 6A part 2. 6A part 2. Oh, damn. It's a Doppler effect, microwaves, EM waves. Now, yeah, for the last couple of days, I still have a lot of students asking me, when it comes to microwaves, right? They thought that when the observer is moving or when the source is moving, the wavelength change or speed changes. That one is only for the sound wave. For EM waves, it doesn't matter which one's moving, right? Both the wavelength and the frequency are changing, right? As long as one of them moves, right? Yeah. Okay. So your equation, the standard equation, would have been del F over F equals to del lambda over lambda equals to V over C. Like, this would have been the standard equation. That means as long as one of them is moving either towards or away, and you can't tell from the equation, the frequency is gonna change, the wavelength is gonna change too. Yeah. All right. Good. The thing here is that it looks like the equation has been changed to this 2 times of V over C. So you get like a 2 times here, but there's no 2 times there. So why is there a 2 times here? Like, why no? Right? Why is that 2 times here, but there's no 2 times in the original equation? Why is that 2 times here? Because this is the double Doppler effect, right? The wave going towards the car and the wave coming back from the car, right? So emits and then reflect off and return back to the device. That's why there's a 2 times here, right? Then they ask you explain for the reason for the frequency change, right? This is just simply the Doppler's effect, right? But you don't go and mention about, oh, the car is moving away, so the wavelength changes. It's actually both the frequency and the wavelength changes. Yeah, for EM waves, that's what happens. Okay, right? So take note of that. But the question is asking for, why is there a factor? Okay, I just answered the question. Right, the factor of 2 is because, right, there's the radar gun to the car is 1 Doppler effect. Reflect off the car back to the radar gun is a second Doppler effect. You write it like that, it's okay. 1 mark they'll give you. These 3 points here. Yeah, this one here will be, you have to describe the Doppler effect. So the Doppler effect is happening, right? When there's a relative motion, right, between the source and the observer. That means you give it very generic, right? There will be a change in the frequency and there will be a change in the wavelength, right? That's observed. Okay, that's the reason why that's it. Yeah, right. Let's see the answer key here. Let's see. Yeah, as in the answer is just describing the Doppler effect. 6, right? 6A, yeah, then mention the Doppler effect like this, right? So there's relative motion, right, between the source observer, right, the reflected wave, right? So yeah, okay. So the idea here is that for EM waves, frequency and wavelength will change, but frequency increase, wavelength will decrease. For this one here, for EM waves, right, frequency increase, right, wavelength will decrease.
Then for sound effect.
Sound is depends on, yeah, what's the one that's moving, what's the one that's changing, and whether is it moving towards or away. Okay.
Is that
Yes.
it's Doppler effect? Is that one?
3, I mean, that's 1 mark. Yeah, that's the Doppler effect. If you mention Doppler effect is 1 mark. Yeah. Yeah. So the
One here. That is zero. What are the
okay. All right. How about one last one? One last one. Okay. One last one. Wait. Let me give it to you.
Wait, Sam, you know when you have the topic in the power rate indicator, then you have to divide by
Yeah.
four.
Okay.
That was a rule. Because so many people.
You have to keep up to it, right? You have to keep up with it, right? And not, yeah, I told you already, it will snowball, right? What? Anyway. Okay, so I have a question here as to why the Earth. Okay, so the Earth, right? Where does it absorb radiation from? Absorb from where? Absorb from where, Taylor? Absorb from where? The sun is all around the Earth, is it?
Yeah.
Right? So how does the radiation from the sun comes towards Earth? It goes through the disk, right? It passes through this disk, right? So the solar radiation goes through this disk, right, and falls onto Earth. Like, if whatever it is, this is like the simplest way of calculating the amount of radiation that we get from the sun, right? Okay, so how big is this disk? How big is this disk? Yeah lah. So the disk area is the same as the, like, you treat the like, is it pi r squared?
Yeah.
Yeah, it's pi r squared, right? So it's pi r squared, okay? Right, pi r squared. So this is r, right? So this right, that the Earth receives the power from the sun is pi r squared. Okay. Then how does the Earth emit this power? Yeah, so when it emits throughout the whole thing, right? So during emission, right? During emission, the Earth emits it in all direction, like, on all the surfaces, right? Like this, okay? Right, it looks like hairy ball, right? So the Earth, yeah, the Earth emits it outwards like this, right? Like, what is the total surface area when it emits? It's 4. No, that's
4/3 pi r.
4. That's the volume of a sphere, bro. So that's why you're all confused. That's why you're all hella confused. The surface area of the sphere is 4 pi r squared. I was almost going to throw a sphere at you. Somehow you're very confident, 4/3 pi r cube. Is it? You're injured. If you're not, I will. So radiation comes in one area, but Earth emits out over four times the areas. That's why the intensity of the Earth radiation, like intensity of Earth radiating, right, is S times 1 minus alpha over 4. Yeah? That's why you divide by 4 lah. I mean, if you're asking me why is it divided by 4, this is the reason why. Okay? Okay.
You just said I don't know what S the right. Hey, you I already
S. What does it represent? It's 1360. Yeah? No, is that what you mean? 1360? Uh-huh. Yeah, it is. It is intensity from the sun. Like it is watts per meter square, right? Yeah. Like the reason why it's 1360 is because, like, from the distance of the sun, right, the solar radiation from the sun, right, by the time it reaches Earth, right, the intensity is 1360 watts per meter square. Every meter square, right, at this distance will receive 1360 watts, right? So in order to calculate the total power that the Earth receives, we use this area here, right? So like, yeah, this 1360, right, like this is intensity. I know intensity is power over area, right? But what was this 1360 from? This power was from the sun, right? That's where the power is. Okay, but what is this area? This area is the gigantic area of this sphere, this entire sphere here, like this, right? Then when you take this, like, 1360 and multiply to the pi r square, which is like the area, but that's the area that is exposed to the sun, that the Earth is exposed to the sun. So we take this 1360 multiplied by pi r squared for the amount of power that the Earth receives. Right? Yo, you there? Emily, you get it, right? So then you got to remember this, okay? Then what does the Earth do with the power? What does the Earth do with the power? Right, it emits it out into space, right? Like how much does it emit in total? Does it emit the same amount that it absorbs? It emits exactly the same amount it absorbs. But do you know why? Think about this. Think of your head as Earth, okay? Imagine your head is Earth, and you're receiving sunlight in this direction, okay? Right? Like if you emit the heat away, you better emit the exact same amount that you're receiving, right? And the reason is, what happens if you receive more and you emit less? What will happen to your head? Yeah, overheat. If you receive less than you emit more, then you will freeze over. But the Earth has been a constant temperature since what? No, as in that's got nothing to do with global warming. Like the Earth's human, like, presence is like a fraction in time of the Earth's like lifespan, right? The Earth has had a constant temperature for millions of years, since the time of the dinosaur until now, right? It's about 15 degrees Celsius. The temperature didn't change. Yeah, the average temperature never really changed. You get what I'm saying? Yeah. No? Yeah. I mean, that's pretty much it, right? So the idea here is, therefore it must emit the exact same amount it absorbs. Wait, there's one question that I want to go through, right? Not this one, right? I want to go through this paper 2 one. Just give me a short. Let me just double check whether is it there or not. I just want to make sure that I got it. Hang on. Because I got a feeling. I got a feeling. Wait, this telegraph. You haven't seen this in a while. Huh? Last year's prelim? Shit, okay.
Yes.
Then it's not gonna come out. Yeah. Why are you so happy about something that is actually easy to do? Yeah. Yeah, dude. Okay, this one, you okay with this? This standing waves, right? Standing wave in the tube, one end open, one end closed. Wait, I want to go and look for that question. There's that one question. Hang on, this question. I think I brought out this question in during the revision. But I've not seen it in the school test recently. No, right? No school test, no prelim come out of this, right? Okay, there you go. Right. So just remember that this exists, right? Just remember that this exists. They did say that these light rays are headed towards which one? The second order maximum, right? They're headed towards the second order maximum. That means on the screen, right? If the screen is very far away, right? The screen is very far away, right? These guys are headed towards the n equals to 2, right? Okay, just remember that even if it's diffraction grating, even if it's double slit or whatever it is, right? If it's at n equals to 2, the adjacent slits, the light rays, have a path difference of 2 lambda. All right. So you know, I'm kind of like hoping that this comes out, right? Cause yeah. So just remember that if it's n towards n equals to 2, right? Then the path difference here, sorry, this one here, that you got two paths here, right? One path here, right? One path here, and then another one here like this. Like the path difference, one of them is longer than the other one by 2 wavelengths, right? Then how about the next two, right? The how about the next two, this one and this one, right? It'll be this one here, right? Okay, you need to drop the perpendicular. You get this? Right, it's also 2 lambda. You get that?
So if it's n equals 3, it's 3.
So what?
If it's n
Yeah, if it's n equals to 3, then the path difference here will be 3 lambdas. But adjacent, so let's say you're looking at the bottommost ray, Mingler, right? You're looking at the bottommost ray compared to the top one here. What's the path difference between the first and third? I mean, this one is 2 lah, bro. So no, this one is 2, and then this one another 2. So the top one and this bottom is 4 lambdas, right? Okay, understand this, Okay, good. Then the next one is, do you see the triangle here, guys? Do you see the triangle here?
Yes.
Okay, so if you see the triangle there, right? If you see the triangle there like this, okay, hang on, right? Do you see there's a right angle triangle? Right, you see there's a right angle triangle. Hang on, let me just right angle triangle like this.
60 marks. So actually,
You'll be embarrassing.
Okay, hang on, right? There's a right angle triangle. This is 2 lambda, right? Okay, do you understand that this is theta?
yes.
Right, they tell you that the theta is here, right? But when you do the geometry, do you see the theta there? Right, so that's the theta there, right? This is the theta to the second order, right? That's the theta to the second order, right? To the second order, right? Okay, so which is basically equals to 2 times of the theta of the first order, right? Approximately, right? So if this is double slit, if this is a double slit, do you see that? Okay, I mean, okay, let's not call it the double slit, right? Let's say this is diffraction grating. Diffraction grating is not double, so diffraction grating. So diffraction grating, this is the distance between the two slits, right? Right, this is the distance between the two slits. What's the relationship between d lambda and theta? What's the relationship between d, theta, and lambda? D sine theta 2 equals to 2 lambda, right? This is how the diffraction grating equation was derived from this diagram, right? So am I right to say that you have not seen this in any of your recent tests or any of your CTs or any of your, right? So, you know, right? So do the questions that you are not familiar with, right? Yeah, but it's very hard for me to go and tabulate which ones have you all been tested on before, right? And which ones haven't come out yet. Because for the, I think, yeah, for the previous batch, one of their tests had this. Yeah, but I don't have a collection of all the tests. I have a collection of all the prelims. Okay, I have about 10 more minutes, 15 more minutes. Is there any last call for any papers or any questions? Come on. Any last call? Come. Last call, last call.
At this rate, 0 bar. Rate, no real bar.
Okay, I want you to take note of this. I don't think you all have finished all the paper threes also, right? So I have to do the paper threes after prelims also, right? Yeah, I still have to do the paper threes. You guys better start churning out the practice. Like don't sit down to revise anymore, okay? Like practice. Learn how to answer questions. That's more important. Like I know it sounds very uncomfortable, but a lot of people like they just keep thinking that I need to revise, I need to revise. Don't do that. I'd rather you be very good at answering questions, right? Not, I mean, if your definitions is kosong, definitions can be fixed in one day one. Like you just sit down, look through the definition of every chapter, you'll be fine. Okay? Yeah. If you need to spend that one day after the prelims, do that one day after prelims. Okay? Just go and memorize all the definitions in one sitting. Don't spend 2-3 days on it, just one day. Then the rest of the time practice only. There's nothing more important than just the definitions first, right? Everything else can be covered with practice. So please, right, remember to do practice. You know I don't do practice in class, right? I feel very uncomfortable looking at y'all do practice while y'all punching in a calculator. I cannot take it. Every time I see y'all, can y'all punch correctly or not? Never bracket, then I have to go and go through that ordeal. Right? No, don't abuse my time. Okay, then
What is far?
what?
What is far? You reach infinity.
Far point?
Yeah.
Yeah, infinity lah. That's a damn annoying statement to use. That's a damn annoying statement. Hey, if there's no last call, right, I'm gonna call the lesson done, alright? If there's no more last call, like, that's it for me. Anyone else got anything else?
One mark.
Huh? For what? What is far point? There was one question just asking what's far point. That's infinity, image infinity. What in the world?
At least one mark.
Uh, okay, Erin, Gerald, Calvin, Emily, any other questions? Yeah, the last guy standing.
Hey, Vegas choosers.